All right, so what we're going to do is really have a crash course in exercises 10b through to 10g, I think it is. So remember, what we're doing is we're dipping back into those exercises and looking at the circular components of them. So let's give a couple of questions a go. The depth of water x meters in a tidal river t hours after midnight is given by this function here. Find the rate at which the depth is changing at. Okay, so notice that this says the rate at which the depth is changing. So not the depth, but the rate at which. Okay, so make sure you read these questions extremely carefully. Okay, so to get the rate in which the depth of the water is changing, we need to find x dash t. So here's our original function here. So remember, what we do is we use this thing here, multiply the coefficient by that number there. So it's going to be 3 pi on 12 cosine pi t on 12. So again, don't forget to use your formula sheet on that if you're not quite comfortable. That plus 1 basically cancels out, as it would like if you had a function like f of x equals x squared plus 2. Most of you guys, I hope, would say that the derivative is 2x with the constant cancelling out. But I've seen some students with trig functions wondering what to do with that plus 1. Well, it's no different, girls. Okay, so here's our derivative. Let's just tidy it up one more bit here. Pi on 12 cosine pi t on 12. Okay, so find t hours after midnight. So this is 4 hours after midnight. So what we're going to do is x dash 4 equals pi on 4 times cosine, what's that, 4 pi on 12. Now that's the same as, what's that, pi on 3. Cosine of pi on 3 is the cosine of 60, which is a half. A half multiplied by pi on 4 is pi on 8. You guys might need a few more steps than that in between just to help you out with that one, but I'm pretty comfortable with that one. Now, because it's a rate, we've got to give a unit because it's an applied thing. So we're going to say pi on 8 meters per hour. All right, this time we're going to bang 2 in, and that's going to be how many hours after midnight? That's going to be 12 plus 2 is 14. So we're going to do x dash 14. Pi on 4 times cosine. What are we doing here? 14 pi on 12, which is pi on 4 multiplied by cosine of 7 pi on 6. All right. So the cosine of 7 pi on 6, that's down here. On 6 is 30, which is root 3 on 2, and that's negative. So it's going to be pi on 4 times negative root 3 on 2, which is equal to negative root 3 pi over 8 meters per hour. Okay, and now for the average rate of change of the depth of water over the first 6 hours. So remember, what we do for average rate of change, it's a well-written question because notice how we've swapped from derivative, found the derivative, now we're going to the average rate of change. And remember, we talk about the average rate of change in terms of the original function, not the derivative function. Okay, so what we're going to do is to find the average rate, we're going to say that is equal to x of 6, take away x of 0, all over 6. Now, x of 6 is going to be 3 times sine of pi on 2 plus 1. Let's chuck some brackets in here, take away 0, 3 sine of 0 plus 1. Do I need another one? Open, open, close, close. All good, over 6. All right, now this one here, so the sine of pi on 2 is here. That's going to be 1. So that's 4. Take away sine of 0 is 0. 0 plus 1 is 1. So that's going to be 1 over 6, which is 3 over 6, which is half a meter per hour. So the average rate of change between or over the first 6 hours is a half a meter per hour. But if you want instantaneous, you're going to use calculus. Average rates, use the original function. Okay. And so again, you can see here that the function looks a little bit cumbersome and clunky, but actually when you jam in the values, you'll find that your exact values work out quite nicely on this. All right, I definitely remember this problem from last year, and it's a tricky one. Okay, so the height above the ground, h meters, of the central point of the path of a skipping rope as it's being turned by M, as she works out in the gym, pre-COVID-19 obviously, is found by using the equation h of t equals a cosine nt plus c, where t is the number of seconds after the skipping rope has begun to turn from its starting position resting on the ground. All right, during the skipping activity, the maximum height of the rope reaches 1.8 meters and it takes 2 seconds for the rope to complete a full swing. All right, here we go. This is what I think happens here. So we've got this cosine function, and I think it's got to start at the origin. And what it's going to do is the rope comes up, reaches its maximum point, and then comes back down again to the ground. Okay, and that's the model of M turning the rope. Okay, so the rope starts to swing. Okay, if you imagine the skipping rope, so here would be the skipping rope, and it's sort of like dangling on the ground. So rope goes around, and I know that that's an oval, should be a perfect circle, comes around to the top, reaches the top point, and then comes back around again. Okay, so let's work out some of these values. All right, so we've got h of t equals, well, it tops out at 1.8, so we're presuming that the mean line is going to be 0.9. Okay, so that's the first thing to note, is we're going to shift this thing up to 0.9. Its amplitude is also going to be 0.9 because it goes from 0.9 to 1.8 and 0.9 down to ground level 0. That's 1.9. Now it's a cosine function that's been inverted, so that's going to be a negative value. And what's our n value? We want it to repeat 2 seconds. It's a fairly long skip. Oh, she's pretty slow. I mean, this is 2 seconds. 1, 2. Maybe that's quick. I don't know. Anyway, I'm not disputing the question. Standard period of cosine is 2 pi over n, and we want the period to be 2. That means n has to be pi. So pi n. There's my function. So a equals negative 0.9. Note that the amplitude is 0.9, but the a value in this case is equal to negative 0.9. Our n is pi. Our c is 0.9. All right, so this is a really important question here. The time at which the maximum rate of change in the height of the rope occurs. We want the maximum rate of change, okay, the maximum rate of change. So what we're looking at here is, if we imagine the derivative function, okay, what we're looking for is when the derivative is at its maximum, okay? When does it change the most, okay? And if you sort of understand what's going to happen, the rate of change is going to be at its fastest. When's it going to be? It's going to be here and here. All right, now why is that the case? Well, if we look at, let's get its derivative. First of all, let's get the derivative. So h dash t equals. All right, so what we're going to do is pull this pi out the front. So that's going to be 0.9 pi. It's going to be sine. Cosine goes to sine with a negative, so that negates the negative. Pi n constant chops out. Okay, so this function here represents the rate of change. Okay, now what we're doing here is we've got basically a sine function, It's got an amplitude of 0.9 times pi, so that's roughly 1 times 3. So it's got an amplitude roughly of 3, and it's got a period of 2. Okay, so that's its period 2. So what's going to happen here is the standard sine function, so starts at the origin, and we're going to put 2, 3, goes up, down, down, up. That's what h dash t is going to look like versus t. But what we're looking for is the maximum rate of change. Okay, the maximum. When is the rate of change at its highest? Now here we've got the highest rate of change because its rate of change here is 0.9 pi. Okay, that's its rate of change here. But here's another really tricky thing. Its other rate of change, or its other maximum rate of change, is down here at negative 0.9 pi. Okay. Now remember, rates of change, when we're talking about the rate of change, it's independent of the sign. Okay. This is negative 0.9 pi, but actually they're both the same rate of change. Okay. They both have a rate of change of 0.9 pi at that point in time. So we're going to take both of these values. So that's when the maximum rates of change occur. Now, how can we do that? Well, another way of doing this problem is actually getting what we call the double derivative. Okay, and so what I'm going to do is get a derivative of this. So we're going to go 0.9 pi squared, not sine again, back to cosine again, pi n. All right, now to do this, what we're going to do is find out when the double derivative is equal to 0. Okay, 0.9 pi squared cosine pi n. All right, and so what I'm looking for is these zero gradient points on the first derivative. Okay, and that's when the rate of change is going to be at its maximum. All right, so let's solve that when it's equal to 0. That means 0 equals cosine pi n. All right, and what we want to do is find out when cosine is equal to 0. So when does that happen? Well, cosine is at 0 here and here. Okay, so what that's going to be is we're going to say pi n equals pi on 2 and 3 pi on 2. All right, let's solve for n and see whether this is enough solutions over the domain. If I need more solutions, I'm going to start to generate them. In fact, I'm going to talk about the number of solutions here as well, because that's also an interesting problem. Okay, here we go. I'm going to say n is equal to, I'm going to divide by pi, which will cancel out that pi. So n is a half, n is 3 on 2. And that means, so we're going to get back to here again, which is pi on 2, 3 pi on 2. This is going to be like 5 pi on 2. So 5 on 2 would be the next solution, then 7 on 2, then 9 on 2, etc., etc. Now, nowhere does it say in the question how long she actually skips for. Okay, it doesn't say that at all. So it's interesting to note then that we can give a general solution here. We're going to say that t is equal to, what are we going to say? It's equal to, let me think about this. So the time when the rate of change is going to be at its maximum is a half. So like at a half second first of all, and then we're going to add plus z positive, where, no, not z positive, plus n. So t is equal to a half plus n, where n is an element of z positive. That's where I'm getting confused there, z positive. And now let's see if we can grasp what I've done there. So I've said that these are all the times when the rate of change is going to be at its maximum, okay? So it's at a half, 3 on 2, 5 on 2, and there's nowhere in there that says she skips for, say, like 10 seconds or 20 seconds or 100 seconds. So I'm going to give a general solution, okay, and say that it's going to be a half plus n, okay, where n is an element of all z positives, and I can union that with 0, can I? Yes, I can. Right, so I'm going to union that with 0 to let someone put 0 in and all the other Z positives, so 1, 2, 3, 4, 5, 6, 7, 8, 9, like the counting numbers. All right, so let's see what happens. If I put in 0, I get a half. If I put in 1, I get 1.5 or 3 on 2. If I put in 2, I get 5 on 2, 7 on 2, 9 on 2, and I've got all of my solutions there. So the time in which the maximum rate of change occurs can be worked out here. T is equal to a half plus n, where n is an element of Z positive, but we're going to include 0 as well. Pretty difficult problem, that one. Okay, that one is tough. Beware of this one here. Just a little tip, it did come up in last year's exam. All right, so some more tricky problems here. Example, using calculus, determine the coordinates of the stationary points if y equals 3 cosine 3x over this domain. So we have to use calculus for it. I can't sort of sketch the graph and go, there's a stationary point, there's a stationary. I've got to use calculus to answer this question. That's what it says here. All right, so the first thing I'm going to do is get dy dx, and that equals -3 sine 3x. All right, now what we're going to do is find out when the stationary points occur, which is when dy dx is equal to 0. So 3x, so when is sine equal to 0? That is going to be here and here at pi on 2 and 3 pi on 2. Okay, what have I just done? No way. That's going to be, I'm thinking of cosine there, that's going to be at 0 and pi. Now, what's my domain? It's negative pi to pi. And what I want to do is do 3 cycles of this. So what I'm going to do is keep generating solutions. So that's going to be 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and 6 pi. I think I've generated too many solutions. It doesn't really matter. Okay. Right, now I'm going to do a solve for x here. So x is equal to 0, pi on 3, 2 pi on 3, 3 pi on 3, which is pi. Okay, so there's my positive solutions. Okay, and now what I'm going to do is consider the negative solutions. So I generated way too many solutions. I mean, like slightly embarrassing there that I couldn't see that, but it doesn't really matter. I mean, yeah, that's gone, and that's gone. Okay, so yeah, you always feel like, you know, you can generate too many solutions and then just chop them out at the end. Right, so to get the negative solutions, I'm going to move backwards, okay? And what each one of these, it'll just basically offset the positive version of it. So we're going to get one at negative pi on 3, negative 2 pi on 3, and negative 3 pi on 3, which is negative pi. So there's all our solutions to this problem. So that's where it's going to have 0 gradient points. I'm just going to use my calculator to check this one. So define f of x equals cosine 3x. If f of x, solve it please for 0, x, and I want you to search between negative pi inclusive, and we do need to be careful about those inclusives there because of the fact that it can equal pi in this case, to pi please. Okay, so we've got 0, negative pi, pi, and it does chop around a little bit here. I don't know why it doesn't give the solutions in order. Someone might have an explanation for that, and I don't know why, but there's all the solutions there anyway. All right, determine the coordinates and nature of stationary points if this is my function. Okay, All right, get ready for this one, girls. This is a bruiser of a problem. Okay, so what I'm going to do is get the coordinates of the station. Let's do this. Let's get the stationary points first of all. So determine the coordinates of the stationary points, and then I'm going to worry about whether they are max, min, or inflection. Okay, I'm going to do that later on. Okay, so the first thing I'm going to do with this is get its derivative. So f dash x equals, in fact, before I jump in there, I'm just going to give the equation a nip tuck. F of x equals 2 sine x, take away 2 cosine squared x plus 1. Okay, now I'm going to f dash exit, which is 2 cosine x. This one here, it's going to be negative 2 cosine squared x. I'm just going to yank this out and chain it because I'm not feeling really confident with this one. So I've got y equals negative 2u squared. So again, note that that can be written as y equals negative 2 cosine of x all squared. Okay, so that's another way of writing that function there. So I've got negative 2, and I'm going to do a u sub on the cosine. So u equals cosine x. Now let's get dy du equals negative 4u, and du dx equals negative sine x. Okay, multiply them out, and I get 4 sine x with a u sub, which is cosine x. So I'm going to get plus 4 sine x cosine x. Oh, that's pretty messy. I'm not even happy with that cosine. Okay, the 1 just chops out on the derivative because the derivative of a constant is 0. Okay, so here we go. All right, so the coordinates and nature of the stationary points. So the stationary points occur when f dash x equals 0, so let's do that. Okay, and you might be thinking, look, how are we going to move forward on this? Like, how am I going to solve that? All right, and invariably, girls, it comes back to actually just using the null factor law. So what I'm going to do is factor out across the two terms what I see as the common factor. So 0 equals 2 cosine. Now that's going to be 1 plus 2 sine x. All right, so let's go ahead and solve each of these. So I've got 2 cosine x. Got to put the x there. 2 cosine x equals 0. Now we're going 0 to 2 pi with no dilations, which is handy. So 0 to 2 pi is going to be, what are we doing? Cosine here, there, and there. So that's going to be cosine x equals 0. So I'm going to divide that by 2, and x is equal to pi on 2, and x is equal to 3 pi on 2. Right, and then we're out of domain. Right, now what I'm going to do is solve this, and notice how beautifully this question is written, because 1 plus 2 sine x, this part here or this part here could be equal to 0 according to the null factor law. So we're going to say that's equal to 0. Sine x equals negative a half, and it just so happens that this turns out to be an exact value. So when is sine of x equal to negative a half? Well, it's going to be over here, which is 7 pi on 6, as well as over here at 11 pi on 6. So x is equal to, in this case, 7 pi on 6, 11 pi on 6. So there's our 4 stationary points. Okay, so 1, 2, 3, 4. Okay, now we need to work out what the coordinates of these stationary points are. So I need to work out what the y values are for each of these values of x. All right, so I'm just going to note them all down. I've got pi on 2, comma something. I've got, what's the next one in the list? 7 pi on 6 is the next one, comma a y value. Then I've got 3 pi on 2, comma something, and 11 pi on 6, comma something. Now, to work out the y values there, what you would do is pop them into the original function, right, which shouldn't be too bad. It's pretty tough. Yeah, in theory, we could be doing this. Like the pi on 2 and the 3 pi on 2 is going to be not bad. I'm going to speed this up on the calculator a bit, girls. I'm going to define this function and actually just jam in these to get the y values a bit quicker. Okay, so let's do that now. Define f of x equals 2 times sine of x, take away 2 times cosine of x all squared, take 1. Okay, now we're going to do f of, let's just see whether it went in correctly. Cosine x all squared plus 1 negative, yeah, that looks good. Okay, so f of shift 0 pi on 2 is 3. That would have been nice. Look, I probably could have done that without a calculator, but getting a bit late in the night. 3 pi on 2, that's negative 1. I'm making myself look a bit foolish. Hopefully these 7 pi and 6s are going to be a little bit more unusual. Not really. Same value. Okay, so what have we done there? So again, you can do that by hand feasibly, girls, by throwing those values into the original function. I just didn't feel like doing it. Okay, now what else do we have to do? We've got to describe their nature. So we've got to say whether this is a maximum or a minimum or an inflection. So let's have a think about that. Now, that is tricky because if I told you, hey, girls, just thinking of this function here, you know, what do you think it looks like? Most of you will look at that and go, wouldn't have a clue. Okay. And yeah, I definitely agree that that's going to be really tricky to work out. So here's a good strategy to use when we're trying to work out the nature of these points, and I'm not allowed to use my calculator. All right. So what I'm going to go to is I'm going to go to f dash x, and I'm going to think about this version of f dash x. I'm going to rewrite it now. F dash x equals 2 cosine x 1 plus 2 sine x. The way I'm going to think about this is one function here being multiplied by another function. So why don't I sketch both individual functions and see where this goes? Okay, so stay with me, girls. Haven't lost the plot. So this is 2 and negative 2. This is pi on 2, pi, 3 pi on 2, and 2 pi. And it's a positive cosine. So it's going to do this, 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 and this. There's my first function. All right, here's my second function. We're going to go up 1 on the standard sine function and 3, negative 1. There, 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 there. Okay, now let's check a few things. All right, so what should happen here is if this is my gradient function, so this is f dash x, okay? And, oh no, it's not f dash x, it's the two of them f dash x will be this function here, this one here multiplied by this one. So here we've got 0 multiplied by whatever this is here. 0 multiplied by 3 gives us 0. So f dash x would have a 0 gradient point at pi on 2. Da, 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 da. Okay, there it is, 0 gradient point at pi on 2. It should have one also at 3 pi on 2 because 0 multiplied by whatever this value here is, -1, is 0. So here's one at 3 pi on 2. Now it's going to have another 2 0 gradient points. One here, just after pi, okay, because that's 0 multiplied by whatever that value is. I wonder how far after pi. Well, perhaps it's 7 pi on 6, just after pi. Now over here, it looks like it's also got one just before 2 pi, because 0 multiplied by whatever this value is gives us 0. 11 pi on 6 perhaps, okay? So there is confirmation that this is right, this is absolutely correct. Now here's the piece de resistance. What we're going to do is work out the nature of these stationary points. So there's going to be a stationary point here at pi on 2. Now what I'm going to do is work out what the gradient to the left of this point is going to be. I know it's going to have a 0 gradient here. To the left is going to be a positive multiplied by a positive. That's a positive. Okay, now to the right of this point, or the 0 gradient point, it's going to be a positive multiplied by a negative. That's a negative. This point here has to be a max. All right, let's go to the next point, which is in the list, which is 7 pi on 6. It's this point here. All right, so here at the 0 gradient point, we're going to have 0. This is going to be a positive multiplied by a negative. So it's a negative. At the 0 gradient point, it's going to flat spot. And then to the, where are we here? It's going to be a negative multiplied by a negative. Right, and a negative multiplied by a negative is a positive. This one here is a min. All right, 3 pi on 2 is here. Negative times a negative is a positive. So that starts with a positive. Flat spots at the 0 gradient point, and then it's going to be a positive multiplied by a negative, which is a negative gradient. That one there is a maximum. All right, and I'm predicting that this last one is going to be a minimum, but who knows? We've got a negative, a positive multiplied by a negative is a negative. So that is a negative gradient. Then it flat spots, and a positive multiplied by a positive is a positive. This thing here is a min. Okay, so there you go, girls. And that's a great way of just finding out what a function might look like when you've actually got no idea what the function looks like. I wouldn't have a clue what that looks like. Wouldn't have a clue. All right, let's get confirmation on this. So I'm pretty keen to see what this function actually looks like on GeoGebra. So let's do the big reveal. All right, so here it is, folks. What I've got here, I'll just pause this for a sec to set. Okay, so we said this function had 4 stationary points between 0 and 2 pi. So let's reveal the function. Come forth function. All right, so let's check whether we were right. So stationary point, 1, 2, 3, 4. 4 stationary points. We said the first stationary point at pi on 2 was a maximum. Sure is. We said the stationary point at what looks to be a bit past pi, 7 pi on 6, was a minimum. Sure is. Okay, we said that this one here was a maximum stationary point. Sure is. And we said that this one here was a minimum, and it sure is. All right, let's fix up a couple of bits of terminology as well. So in here, the maximum value, let's have a look at it again and just check. So that is actually the maximum value of the function. So we can say that that's the maximum, or it's a maximum. This is certainly the lowest value in the function, so that's a minimum. This thing here is also a maximum, okay, but we're going to call this something different. We're going to call that a local maximum. This one here, we're going to call that a minimum. So we can call that a minimum again. So we're going to change one thing in our definitions here. And I should have probably picked up on this when I declared them both maximums. This one here is also the absolute maximum of the function. This one here is a local maximum. Right, so much to that question. That is incredibly difficult, that one. All right, this one here will be a little bit more accessible, shall we say. All right, we've got f of x equals cosine 2x. All right, now this is the classic question, and often it is tech active. So I'm just going to show you what many students will do on this. Define f of x equals cosine 2x. They'll go, oh, so it's over that restricted domain. So we're going to do f of pi on 6. Note that value down. And 3 pi on 2, -1. And so they're going to say that our range was whatever that previous value is, -1 up to that previous value. Okay. Now, don't do that. Okay. Make sure you have a look or sketch the function. Okay. That's very important that you do that. All right, so let's actually have a look at what this function might look like. Now, the other thing students do is they go maximum, minimum. Well, that's calculus that dishes maxes and minimums, okay? But this is just saying when is the largest value, or what's the largest value to come out of the function, what's the smallest value. The stuff calculus, let's just sketch this thing. Right, so we've got pi on 2. No, we've got a period of 2 pi over 2, which is equal to pi. Scale is pi on 4. So pi on 4, 2 pi on 4, 3 pi on 4, and pi, 5 pi on 4, and 6 pi on 4. Right, the scale's all skew-if, but I'm not really being assessed on that. So this is what the function would look like. Now, where is pi on 6? Okay, so pi on 6 is a smaller fraction than pi on 4. Okay, so if we compare both of them, pi on 4 would be like 6 pi on 24. This one here is going to be 4 pi on 24. So it would be somewhere over here. Okay. So its value there, you can see here, is already trumped or will be trumped here to get to this point here. Right, so whatever that start point is value, it is the maximum. So like it holds as the maximum for a while. It's like, yeah, I'm the highest, I'm the highest, I'm the highest, I'm the highest, all the way up to here. And then this now trumps it as the maximum value. So we're going to say that the max is 1. It doesn't tell us when it occurs, it doesn't care. So the maximum is 1. Now what's the minimum? Okay, well, it terminates here at 3 pi on 2. The minimum is -1. So not a bad way to finish, and I suppose that's a good question to come in, because those of you who fall in love with calculus for all of these parts here will try to throw calculus at this problem as well, maybe, or do the old sub in the endpoints thing that you do. All right, good luck with that exercise, girls.